All right, thank you so much, guys. I appreciate it. So today we're on lecture 3. We're going to do cells, organelles, and transport. So we'll cover all the cell organelles, okay, and talk about their functions and also the transport mechanisms through the plasma membrane. All right, and we'll cover all that today. So there's 4 major components of the cell, right? The membrane itself, which is the boundary for the extracellular and intracellular material, all right? Then the nucleus is one of the organelles, but we mention it specifically because it is the genetic material, right? And then, of course, the cytoplasm, which includes the fluid component of the cytoplasm, ladies and gentlemen, is the fluid component of the cytoplasm. It was one of the questions you guys had trouble with in the LS module. Cytosol, yeah. And then the cytosol has got the cytoskeleton, which are microtubules that move organelles around or keep organelles in place, right? And then of course the organelles inside, right? So so we'll do all these 4, and we'll talk about each of these in turn, right? And so of course, cytoplasm is cytosol fluid, and then of course, in that fluid you have the organelles which are suspended in there by the cytoskeleton. Okay, the cytoskeleton holds the organelles in place. This is one of the hypothetical cells because it's got all the possible organelles that can happen, that could occur on a cell, except one thing that isn't shown here, which is this long tail-like. Where do we find the long tail-like organelle on cells? Which is the one cell that has it? The sperm, yeah, for swimming. So the flagella, and then of course this is the cilia, right? And this is the microvilli. Where do you find microvilli? Okay, and what's the function of microvilli? Okay, that's very good, because some of the problems also can arose between the differences between microvilli and cilia in the modules. And then of course cilia, where do you find cilia? Which system? Which one? Respiratory system, yes. Respiratory system, and so what cilia does is that it moves materials on the surface. Like for instance, when you trap, particles with mucus that lines your respiratory system, and you could cough it out or sometimes sneeze it out, and that's how you move that mucus by moving cilia. Another situation where cilia is helpful is the oviduct, because the egg doesn't have a tail like the sperm, so the cilia lining the oviduct will move the egg along towards the uterus. So that's the difference between cilia and microvilli. All right? Okay, and this is just a cell in 3D, and we can go quickly through that. You can see the rough and particular, and then some individual body. We'll talk about each of those organelles and their functions. So, of course, you will notice that all the cellular functions are related with all the characteristics of life that we studied at the beginning, right? So, the first one is to make or synthesize proteins and so forth, and all the metabolic reactions that occur in the cell. Those are the functions. That's the number 1 function of the cell here. And those metabolic reactions, because they're not 100% efficient, they give off heat, okay, which is then used to maintain body temperature, right? Because when these reactions are occurring, all the energy from ATP is not used up in the reaction. And whatever remains, the excess of it is what we use to heat the body, to maintain the temperature steady. And then, of course, synthesizing new molecules And cells differ because of the products they make, like the kind of proteins they make. And the proteins are the enzymes, and this will vary the the function of each cell, just based on products that it makes, right? Because they will affect different functions of the organism, all right? And provide a means of communication. Last time I was talking about those glycoproteins and glycolipids on the cell surface that are used as marker molecules for cell-to-cell recognition. And we'll talk a little bit more about that when we talk about the plasma membrane and the marker molecules. All right, but cells need to recognize the other cells, especially in terms of the immune system. It has to recognize your own cells and foreign cells, right? Otherwise, your immune system will just attack any other, cell, and it might be your own. And actually, when something goes wrong with this cellular communication, you get an autoimmune disease where you attack your own, cells, right? So that's very important. Cell recognition, all right, and of course reproduction, which is again related to those characteristics we talked about. Okay, so mitosis, the main function is to increase what? What is mitosis? Just cloning, right? Just dividing cells and you get the exact same cell. So it increases cell number, and it's used for replacing skin, for instance. All the skin, is replaced every 45, 30 days. So all that is mitosis. What about meiosis? What is it used for mostly? Reproduction, yes. In terms of producing what? What does mitosis produce? Meiosis, I'm sorry. What is used in reproduction? What kind of cells? What's that? Like the starts with a G? Gametes, yes, gametes. That's right. So mitosis produces the gametes because they are haploid, right? Because they have half the genetic material. When the male and female gametes unite, then you have a diploid cell, and then you have reproduction. We want to talk about meiosis and mitosis because we covered that a lot in that. So we'll go right into the plasma membrane. This is the boundary of the cell. It encloses all the organelles, right? In the cytoplasm, right, which has the support for the cell contents. The cytoplasm, remember, is the cytoskeleton. So cytoskeleton. Cytoskeleton is what supports those organelles in place. Or movement of vesicles within the cell is the result of those cytoskeleton, which is long fibrous proteins that are like rods, literally, that scaffold things around and keep them in place. You can imagine if you had a balloon and you put little beads in there or something, or balls or little marbles, what would happen to all those things you put inside the balloon with water? You just sort of settle on one side, right? So that's why the cytoskeleton is very important, because it will keep the organelles in certain places, and then movement of vesicles as well within the cell, right? So the cytoskeleton is very important in that. And then, of course, the membrane is selective. It will let certain substances in or out. It doesn't just let anything in or out. So it maintains the integrity of the cell, right? And then, of course, plays a role in communication, which is very important, especially for the immune system, right? That's how tissues are formed as well, because like cells will stick together because they have a common function in forming tissue together with the extracellular material, right? And then, of course, it separates the extracellular environment, which is the interstitial fluid, because it's inter between cells, and then the internal environment, which is inside. So it's very important to demarcate these two, right? Because otherwise the cell is just going to be like all the other fluids, and it's not going to be unique in its function and characteristics too. Right? So, and the nature of the membrane is such that it's fluid. Okay, it's this lipid bilayer with the phospholipid, the phosphor heads facing on the outside and proteins wedged in between. Right? You can imagine if it's like this, and then you get a protein like that, and then these are the tails inside, right? And then you get more. Sometimes some proteins do not go through the membrane, right? It's like that, and then so you might have like that, and then we have the glycolipids and glycoproteins. You see, marker cellular proteins. Another thing you have in there, wedged with the hydrocarbon tails, is cholesterol inside here. Okay. But 20% of the end of the thing is cholesterol in plasma membrane. What kind of compound is cholesterol? From the 4 main compounds we talked about last time. What's that? It's a lipid, yes. Remember, it's the makes the steroids. It's that. Remember the look of cholesterol. It's like this. You got these 4 rings, and then this one is got 5 sides, and then you get the chains on the side. And cholesterol is a long chain on this going out, so I don't have enough board. So you can imagine this being wedged in between these hydrocarbons. The hydrocarbon tails are long like that. Okay, so it kind of gives it that fluidity and stabilizes the membrane. Right? That's what it does. Cholesterol does. All right. And of course, the phospholipids have. I think this was also one of the problems that you had with determining the hydrophilic part in the hydrophobic part. So the hydrophobic part is which part? The tail or the head? The hydrophobic, the tail. Hydrophobic is water hating, right? Okay. Remember, the outside here is aqueous environment. All this is aqueous environment. So that's why you have the heads facing out, the heads facing in. Because the cytosol is also fluid, it's also water. It's an aqueous environment. Okay? So, and the heads are polar because they've got a phosphate group on it, which has got 2 negative charges, so it's polar, right? And then of course cholesterol gives strength and flexibility because it's a 4-ring compound as opposed to just the straight chains on the fatty acids. So it kind of gives stability and strength. So you need cholesterol in there. So you can see all this. And then this will be a channel protein. We'll talk about it later. Okay, membrane channel protein and some other proteins are carrier proteins. They are attached to the actual molecule being moved. We'll talk a little bit more about it when we talk about mediated transport, right? But carrier proteins differ from channel proteins because channel proteins, the size of the channel determines the size of the molecule that goes through it. It doesn't really attach. If it's too big, it won't fit, and if it's not the correct size in terms of the the shape of the molecule, then it's not going to go through, right? Whereas carrier molecules will actually attach to it and then change shape and move the product. So this is the fluid mosaic model with the phospholipid bilayer and the embedded proteins, and also these are the marker proteins. It could be a glycolipid attached to the lipids or a glycoprotein attached to the proteins. Are used for cell-to-cell recognition and cell-to-cell attachment, or attachment to other molecules, which we'll talk about in a little bit when we talk about the cadherin cell. Right? So protein molecules kind of sort of float in there because again it's kind of fluid, the lipid bilayer, That's why it's called fluid mosaic model. So you got the marker molecules here, which we said glycolipids and glycoproteins. Can you see that? The glycoproteins. So this marker molecules, very important for cell-to-cell recognition, right? And then attachment proteins. We said cadherins attach what to what? Anybody remember from the module? Cadherins attach what to what? They attach cell to another cell, right? Cell to another cell. Okay. What about integrins? They attach the cell to what? Well, other molecules. Yeah, they attach, to other molecules, other small molecules. Okay, so they attach to other small molecules. And the fact that when those small molecules attach to the integrins also have a way of affecting what happens inside the cell. So integrins, we could actually say receptor proteins are kind of specialized integrins, because receptor proteins will attach to a ligand from the outside and then will affect the function inside of the cell, right? You see that? Whereas integrins will attach to kind of sort of any molecule, but receptors have a specific ligand, which is almost like a lock and key kind of thing. If the ligand doesn't fit the receptor, there's a receptor site specifically for that ligand, okay? Such as G protein activators. They will, a G protein is a transmembrane protein, and then it's attached to another enzyme inside of the cell that will produce another molecule, which acts like a second messenger. It will then put into effect the function after a molecule attaches on the outside, the receptor. Okay, so those are true receptor proteins. But they, insofar as attachment of a receptor or another molecule affects what happens inside the cell, it's like an integrin. Okay, so receptors will be called specialized integrins because of that. All right, and then of course enzymes that will catalyze certain reactions. And enzymes themselves are proteins. It could be an enzyme that's going right through the membrane, and then it will catalyze a reaction that will affect the proteins inside of the cell. Right? So now we go to movements through the cell membrane. So the first one is diffusion, and we will talk about it. And the definition for diffusion is movement of molecules, right? In what kind of medium? Yes, so? Yeah, high to low. And what's the medium through which we are moving in? A solution, right? Remember a solution. Solution. So it's high to low in solution. And we will talk about the qualities of a solution in a little bit. And then osmosis, so it's movement from high to low in a solution of solid. What is the solid? The solid is what's dissolved in the solution. Right? So it's movement of solid molecules from high concentration to low concentration. And it doesn't non-energy demanding process. Just done it right. And then osmosis, it's movement of what? What is water molecule? In this case, that's the solvent, right? Water is the solvent. How is this movement? From high to low concentration as well. Through what? Through what? Through what? Yeah, selectively permeable membrane. if I ever ask about the definition for osmosis, you're going to mention those 3 things. It's movement of water, which is the solvent molecules, and you got to talk about from high to low concentration, right? And then you got to talk about through a selectively permeable membrane. You're going to mention all those 3 to get full points. From high to low. Through selectively permeable membrane. SPM is selectively permeable membrane, okay? And then we'll talk about mediated transport. Again, in these modules, we kind of had a few problems with this one. Mediated transport, what did we learn from the modules? What kind of transport is mediated transport? Just by the name of it. To mediate is to kind of go between, kind of to like, you know, help out, assist. So whenever anything, a molecule assists the movement of that other molecule, it's mediated transport. Sometimes it could be an energy pump like the sodium potassium pump. Any active transport is some form of mediated transport, right? Active transport, also facilitated diffusion. You know, when a molecule that's being moved attaches to a protein and then it is moved. So facilitated diffusion, and we'll talk about this later on, okay? And then vesicular transport. What are the 2 forms of vesicular transport? Yes. Endocytosis. Now, endocytosis differs in, there's 3 types of endocytosis based on the type of, or the qualities of what is being moved, based on the characteristics of the molecule that's being moved, or the substance that's being moved. So, what's the, you know, kind of like the most common kind of endocytosis that is done by immune cells, like macrophages. What do macrophages do? They engulf. And what's that process when you engulf some solid substance? What do we call macrophages? It starts with a P. What other words do we call macrophages? Phagocytes. So phagocytosis is when we move a solid. Endocytosis when a solid is internalized. So phagocytosis is solids, right? And then the other one, when we move liquids or solutions, yeah, pinocytosis. And we'll talk about each in turn. And so this is fluids, okay? And then the last one is endocytosis. This one has got a helper protein that kind of attaches to that substance being moved. What's that? It's kind of like a 3-word answer with a hyphen in the middle. Receptor transport. Yes, receptor mediated transport. This is when whatever is being moved attaches to a cell surface receptor, and then the membrane just pinches off and it's internalized. But whatever is being engulfed has to be attached to the receptor on the cell surface first. So receptor mediated endocytosis. All right? And then what's the other vesicular transport? Exocytosis is last. Exocytosis. And I'll go through these in turn, okay? Exocytosis is the last one. So we'll cover the definition for each and go through it and some of the properties. Okay, so the movement of solid molecules from high to low concentration, non-energy demanding, until equilibrium is reached, at which point there will be equal distribution of the solid throughout the solution. Right? So we all know what the solution is, all right? It's a mixture of solvent. In this case, the universal solvent is water. Everything occurs, all the chemical reactions in the body occur through an aqueous environment, solution, right? And then, of course, the solid is what is dissolved inside of the solvent, right? So, the more we have solids, all right, the higher the concentration, all right, and the higher the osmotic pressure. Osmotic pressure is the pull of a solution, the attraction it has for water. Remember, water is moving in osmosis from high to low concentration. If a solution is highly concentrated, that means there is more solid and less of the water, of the solvent, right? In comparison, in terms of when you compare how much there is, so there will be more solid and less of the water. So water will, that solution has a pull for more water molecules to come towards it. That pull is osmotic pressure, and we'll talk about it when we do osmosis. So pretty much for any, even for diffusion, so the concentration gradient is the difference in concentrations between two solutions and the distance between them, okay? Because the distance affects how fast the molecules move from the point where they're concentrated to the other point, okay? The shorter the distance, the quicker it will move, okay? And so that's why you have the distance between the 2 points. But pretty much, the more solid, then the higher the concentration gradient compared to the reference point. All right. So the solutions become very important with the osmosis. We'll do that in a moment.
Molecules dissolved in a solution are in constant random motion due to their kinetic energy. One result of this motion is that dissolved molecules become evenly distributed throughout the solution. This tendency of molecules to spread out is an example of diffusion. But how do these molecules come to be evenly distributed? Let's start with a beaker of plain water. What will happen if we now add a lump of sugar to the water? A lump of sugar is composed of many individual sugar molecules, and even as a solid lump, the individual sugar molecules are in motion. When the lump is dropped into the water, it begins to dissolve. Individual sugar molecules move randomly and constantly from the area where they are common to the area where they are scarce. This type of motion, when molecules move from areas of their higher concentration to areas of their lower concentration, is called diffusion. Diffusion continues until all the sugar molecules become evenly dispersed throughout the beaker. The rate of diffusion is affected by temperature, size of molecules, and the steepness of the concentration gradient. Although not specifically shown in this animation, this is one of the processes whereby materials are exchanged between a cell and its environment.
Okay, so that's diffusion, that's raised to principle. All right? Okay, osmosis, we talked about it. It's the movement of solid solvent molecules. In this case, the solvent is always water. That's the universal solvent from an area of high concentration to an area of low concentration through a semi-permeable membrane, or you can say selective permeable membrane. Right? So water, because it's a very small molecule, okay, it can go through the lipid bilayer, even though it is polar, but it can go through. All right? But there are specialized proteins called aquaporins that are transmembrane proteins with a channel that will let water through into the cell. Right? And this happens at a very fast rate when there's an aquaporin on the membrane, which is a transmembrane protein. And aquaporins are very important in which system of the systems we've talked about, just roughly when we were talking about the organs and the systems. Which system do you think aquaporin is very important? The system that regulates fluid content in the body. Which kind of cells? Which system controls fluids in the body? When you urinate, what are you doing? Which system does that? Yeah, the kidneys. So that's the urinary system. That's why in the kidneys, the aquaporins are very important, because when blood is filtered, all the fluid comes out. And then you have to absorb all the fluid, otherwise you pee your blood out completely, all the fluid, you know. So because when filtration occurs in the kidneys, to filter the blood, you have to reabsorb all those fluids. So in order to make a quick movement of water through those, kidney cells, you have aquaporins. Okay? But water can still cross the plasma membrane because of its size, because it's small molecule. Right? So remember we talked about osmotic pressure just a little while ago. A solution that is highly concentrated has more solid molecules in it than compared to water. So it's going to want to attract water towards it to dilute it. So that pressure that attracts water molecules towards this concentrated solution is what is called osmotic pressure. And then, of course, if you want to measure it the other way, the force it takes to stop that water from moving in, that's what osmotic pressure is. Or if you put a selectively permeable membrane and you've got fluids that are equal from on either side, right? And then you put a solute in the other side, then it's going to start to pull. It will create a column of water and it will actually start to rise. Okay, that will be equal to the osmotic pressure of that solution, right? And then, of course, isosmotic, it means the solutions have the same concentration of solid. So there is no net movement of water between the solutions. That's what happens in blood. Blood is pretty much plasma, which is the fluid component, and a whole bunch of what inside? What is inside? What is blood? And we got the fluid. I said that's the one component. What are the other components of blood? What's inside that fluid? Blood cells, a whole bunch of blood cells. So the solution, the plasma, has to be isosmotic with the solution in the cytoplasm of those cells. Otherwise, if there's a difference, water will move in one direction or the other. If the plasma is more concentrated, then water will move out of the cells. White blood cells, red blood cells, and so forth, and they'll start to shrink. And if the concentration in the cell is higher, then water will move towards them until they burst. So that's why homeostasis is very important in maintaining the same pH in blood and all that. Okay, so and then of course hyperosmotic means it's got higher concentration and it will pull water towards it. Hyperosmotic, it means it's less concentrated, therefore water will move from a hyperosmotic solution to a more concentrated solution. Right? So this is why this is important for this. We use a red blood cell in analogy, and one of the things about the red blood cells, if you take a cross section like that on it, just like that, and it has no nucleus and so forth. And the reason for this shape is so that it can squeeze through capillaries. You know, there's small little gaps, small little pores between the endothelial cells lining capillaries. So if it starts to absorb water or if it starts to change shape, then it's not going to be effectively moving through those pores. So the shape is going to be important. Remember, like we always say, structure related to function. So that's why those concepts will matter for blood especially. Because those cells can either burst or they can shrink if they are losing water.
Diffusion is the net movement of molecules down a concentration gradient. This process allows small molecules, such as oxygen and carbon dioxide, to cross the plasma membrane. Most polar molecules, such as sugars and proteins, cannot freely cross this lipid membrane. Although water molecules are polar, they are small enough to pass through the membrane freely. This special case of diffusion that involves the movement of water molecules across a membrane is called osmosis. If a molecule, such as urea, is added to one side of a membrane, it will not be able to diffuse across the membrane because it is both large and polar. Because of its polar nature, it will interact with other polar molecules, such as the water. This interaction reduces the number of free water molecules on the right-hand side. With fewer free water molecules on the right-hand side, there is now a net movement of water molecules down their concentration gradient to the side with the urea molecules. Because more water molecules are moving into this area than are leaving, the water level on the right side will rise. If the osmotic concentrations of two solutions are equal, the solutions are isotopic. However, when the solutions have unequal osmotic concentrations, the solution with the higher concentration of solutes is hypertonic, and the solution with the lower concentration of solutes is hypotonic.
All right. So in this little video, they explain how osmosis works. How does it work? Remember, when we started, we pretty much had the same amount of water on each side, right? With the same level of fluid, right? So how come then, if we have the same amount of water, which means probably the same amount of water molecules, so how come water molecules move to the other side when we added the solid? What did they say happens when you add the solid to the other side? What happens to the water molecules? What's that? Yeah, how is the water less concentrated? That's what I want you to explain. Exactly. She figured that out quickly. That's good. Because you see, we started with the same level of water. When you added solute over here, you still had the same level of water. Now the same number of water molecules. Except because this urea, anything that dissolves in water is polar. Because if it's not polar, it's not going to dissolve. It's going to be like a lipid and it will just go on top. So since water molecules themselves are polar, they will attach to this new polar solute that you just added to it, and then you're going to have less free water molecules in this side. That's why the water molecules will start to move here. That's how it works. You see what I'm saying? The first is the description of osmosis, and this shows how it actually works. Because the water molecules are bound to the solid. So the more solid molecules there is, the more concentrated it is, the more water molecules are bound to the solid. And therefore, there will be less free water. So that means that's what creates the osmotic pressure to pull water molecules towards that solution. So you have an equal number of free water molecules on both sides. Right? So I might just asking the example how osmosis works rather than asking you to find. Right? Don't you think that would be more fun? There you go. So mediated transport. Mediated transport. This is whenever there's a molecule or a protein that assists with the movement of those substances or ions of molecules. Right? So it's movement through the membrane when a protein assists the ion or the molecule to move across the membrane. Right? And there's different forms of it. So because there's a specific molecule that is helping out or assisting with the movement, you're going to have three things, right? First of all, there's going to be competition. You know, if you have the same kind of molecules that can attach to that transporter or the helper protein, then they're going to compete to join it, number one. And then you're going to have, of course, specificity, because not any protein will attach to any other molecule or ion. So it's going to be specific, so that means it will only move certain molecules. That's how selective, in fact, that goes to the concept of being selectively permeable, because it doesn't just attach to almost anything and it goes through. It will attach to certain substances, right? And the third concept is that it's going to be saturated, right? And saturation is going to depend on the number of those carrier proteins on the membrane, right? So it doesn't matter if you have like a high concentration. If you have only 3 carrier molecules, then that's how fast the diffusion is going to go. You know what I'm saying? Because it will depend on the number of. So you got to be able to explain these 3 concepts when it comes to mediated transport: being competitive, being saturated, and also the specificity for a specific type of protein. I mean, specific type of molecule, right? So that's what mediated transport is. It is a finite rate of reaction depending on the number of carrier proteins on the membrane. The more carrier proteins it is, the higher the rate of transport. Right? And then types of proteins. So, like I was saying earlier on, we got the channel proteins. Channel proteins are transmembrane proteins that have a pore for a channel through them that, because of the shape and the size of the pore, will allow certain molecules of a certain shape and a certain size. But a carrier protein, on the other hand, attaches to the protein, or to the molecule, sorry, attaches to the ion or the molecule and moves it through when it changes shape. All right? So you see the difference between a carrier protein and a channel protein, right? Can you describe the difference between the two? Carrier protein attaches to the molecule, changes shape, and moves it through. Like facilitated diffusion is one of those. But a channel has got a pore that has a certain size and a certain shape. So that molecules of a certain shape and a certain size will fit through it. Like the upper pores, okay, will only fit the water through them. Because water has a certain shape of the molecule, it's got a certain size, right? Even if molecules are similar in size, they'll probably be different in shape, okay? Because if it's got different elements, it's going to be different attractive properties. It's going to be a different shape. So it won't fit through the channel protein. See what I'm saying? So this one is the size in shape, okay? And this one is pretty much just the shape of the protein, because it will attach to the it's almost like a receptor kind of and it will still move down the concentration gradient. So carrier proteins will have uniport. I think this is another module problem in terms of describing the different kinds of mediated transport. So what does a uniport do? It will move one in one direction, one ion or one molecule in one direction. And then a symport, sim is same, right? So it will move two or so more molecules in the same direction. Okay, so that means into the cell or out of the cell, whichever it is. All right, and then an antiport will do, anti means against, so it will move one molecule in and another molecule out. All right, and all those are forms of mediated transport, right? So just know those, and then of course anything that uses active transport, because it's got a protein that's helping with the movement. An active pump will move molecules and ions against what? Against the concentration gradient. So that's why it will take energy to do it. When in diffusion, we're moving from high to low concentrations. No energy is required for that. Okay? So active transport requires energy because you're going against the grain. You're going uphill, if you will. Okay? And then another thing that was a problematic in the LS module is the description for secondary active transport. Okay. So I'll give you a scenario of what happens like in the small intestine. After you've digested all the things and there's glucose in there, amino acids and so forth, what happens is that the cells normally pump sodium outside, right? Remember the sodium-potassium pump? That it pumps the sodium outside and potassium inside. So whenever a concentration gradient is created by an active transport system, like the sodium-potassium pump, where you're moving sodium outside of the cell, and when sodium now moves down its concentration gradient back into the cell, and then another molecule piggybacks on it, like what glucose does in the small intestine, and is moving against its concentration gradient, that's what secondary active transport is. It happens when a molecule is actively moved out of the cell to create a concentration gradient. And then when we use that concentration gradient to move back into the cell, and then piggyback another molecule with it, that's secondary active transport. Because it's not really expending energy for that particular movement of that ion or molecule, but energy has already been expended when you were building the concentration gradient. So it's secondary active transport. Okay? So, gotta be able to describe this. And glucose is a good example. Even amino acids, when they are being absorbed, eventually after you've absorbed most of the amino acids, you'll be moving them against the concentration gradient. Because all the cells will be full of the glucose that you just absorbed. But the body will absorb all the glucose that you've eaten, right? Okay, so it will be against its concentration gradient. And it will piggyback on the energy from ATP, from the sodium that has already been pumped using the ATP pump. Okay? So facilitated diffusion.
In the process known as facilitated diffusion, a special carrier protein with a central channel acts as a selective corridor which helps molecules move across the membrane. These special carrier molecules that form the protein channel bind only to a specific molecule, such as a particular sugar or amino acid. Once the molecule binds to the carrier protein, this protein helps or facilitates the diffusion process by changing shape and moving the molecule down its concentration gradient through the membrane into the cell where it is released. Facilitated diffusion is similar to simple diffusion in that both involve movement of molecules down their concentration gradient, and this movement is carried out without any input of energy. However, in facilitated diffusion, the movement of molecules will only take place if it is facilitated or helped by a special protein carrier in the membrane. Facilitated diffusion can occur in either direction depending on the concentration gradient. If there is a higher concentration of the particular molecule inside the cell, the same carrier protein would then transport the molecules out of the cell.
So with this, again, the difference between carrier proteins and channel proteins, these ones have to attach to the protein. Whereas with the channel protein, it doesn't attach. It's just the size and shape of the molecule that will just go through. It doesn't attach to the actual protein that's floating out. Okay? So that illustration kind of addresses that point. The difference between the two. So now vesicular transport. Again, I think we had a few questions being gotten wrong in the LS module because so facilitated, vesicular transport is reserved for very cumbersome molecules, very large molecules. You know, we just described the fluid mosaic model of the membrane and how it's got all these things wedged inside, cholesterol inside, and then those proteins that are wedged in between. And then imagine trying to get a bulky molecule through all that stuff. It's not going to work. It's not going to really work. So for those large compounds, you have vesicular transport. Because vesicular transport is just engulfed, and then it's either internalized or externalized in a vesicle via exocytosis. So vesicular transport is what it's reserved for. Large molecules. Even if they are lipids, but they're too large, they still won't be able to go through the membrane. All right? So macro means large molecules. So that's one thing to note. And we already talked about endocytosis, and we said you have phagocytosis, which is movement of solid, engulfing of solid material into the cell, such as when white blood cells engulf bacteria. That's a good example. Macrophages, when they engulf red blood cells, worn out red blood cells, so that they could be recycled, the material is recycled. Red blood cells, your red blood cells are replaced every 3 months, roughly. So every 3 months, every quarter, you have new red blood cells. Right? And every month, you've got new skin. So all that is a whole bunch of mitosis happening. So phagocytosis, then pilocytosis means a fluid, okay, or something that is dissolved, substance in it, or ions or molecules. All right, pinocytosis is a fluid, and then receptor-mediated, whatever is being engulfed, and this occurs in morning I was talking about low-density lipoproteins, which is going to be one of our cartoons. One of our cartoons for a few ahead. Low-density lipoproteins are very huge, and they get some protein on it, but a lot more lipid on it. But they still can't go through the membrane. So you use receptor-mediated endocytosis. Okay, they have to attach to a certain receptor first, they're engulfed. Okay, and the reason because they are large molecules. So if I ask about what vesicular transport is used for, then you talk about movement of very large, bulky, cumbersome molecules through the plasma membrane, right? And then of course the final is vesicular transport. Why is it called vesicular transport? Because we create vesicles, simple. And then this one is exocytosis. When the vesicle pretty much just unites with the membrane, it becomes one with the plasma membrane, and whatever was in it becomes externalized. And that's exocytosis. And this is an example of a white blood cell or a macrophage engulfing worn out red blood cells so that they can be recycled. The material is broken down and then it's recycled. And then this is just, as usual, a table summarizing all those different transport mechanisms, from active transport and so forth to diffusion. All right? Yes?
I'm confused between mediated transport and facilitated diffusion.
There's no difference. Actually, facilitated diffusion is a type of mediated transport because you get a helper protein weight attached. So facilitated diffusion is a type of mediated transport. So mediated transport, I think that was the problem in the module, because I think people may have said facilitated diffusion when they were asking about anything where a helper molecule is used to move a substance is mediated transport. Whether it be the ATP pump in the active transport or facilitated diffusion when you use a protein, okay, or a carrier protein going through a channel, anything that helps out with the movement of that of a particular ion or molecule is going to be mediated transport. And this is one, facilitated diffusion, the type of mediated transport, right? And the secondary active is also mediated transport. Active transport, also mediated transport. This is mediated. And then this is vesicular, right? Because of the vesicles, right? And diffusion is any solid molecules, and osmosis is any solid molecule. Well, not any, but it's solid molecule, which is one, right? So this is the endocytosis one.
The substances used as fuel by single-celled organisms include other smaller cells, particles of organic material, and large molecules that cannot pass through the plasma membrane. Many single-celled eukaryotes use a mechanism called endocytosis to ingest such food particles. In this process, the plasma membrane surrounds and engulfs the food particle. Cells use three basic types of endocytosis depending on the size and nature of the material to be ingested: phagocytosis, pinocytosis, and receptor-mediated endocytosis. If the material the cell takes in is particulate, such as a bacterial cell or an organic fragment, the process is called phagocytosis. If the material is a liquid, it is called pinocytosis. Some types of molecules, such as low-density lipoproteins, LDLs, are transported across the plasma membrane by receptor-mediated endocytosis. These molecules first bind to specific receptors embedded in the plasma membrane. The receptor molecules are concentrated in an indented pit coated by the protein clathrin. When sufficient target molecules accumulate in the coated pit, the pit deepens, seals, and is incorporated into the cell as a coated vesicle.
All right.
Exocytosis is the reverse of endocytosis. This process results in the discharge of materials from membrane-bound packages that migrate to the inner surface of the plasma membrane, fuse with the membrane, and then release their contents to the outside of the cell.
Okay, so the LDL, like I was saying, because it's a huge molecule, it will first attach to a receptor. And the reason for that is that because the pathway that receptor for the LDL is, there's a protein called clathrin that surrounds that area. Because I guess that protein will be necessary for processing the LDLs. because what LDLs do is transport cholesterol into the cells, and high density lipoproteins or the other ones are smaller, almost like the water molecules, and they go through. They also carry cholesterol. Okay, but the LDLs, because of their size, even though they've got more lipid in them, they still need vesicular transport. Right? Okay, so now we talk about the cytoplasm in the cellular organelles as well. Okay, so it's pretty much the material between the cell, and we already talked about it, how it's made up of the cytosol. The other half is the cytosol, and of course the other half is the organelles. And all these organelles are suspended inside of that fluid medium, the cytosol, by the skeleton. And the cytoskeleton is those rod-like proteins that literally hold these different organelles into place. Otherwise, they all just sort of settle down somewhere because it's a fluid medium, right? Okay, so, and then these are the different kinds. Microtubules made by tubulin, actin filaments as well made by actin. The protein is actin, and then intermediate filaments provide mechanical support of the cell so that it's a certain shape, so that everything doesn't collapse in on itself, right? And I think there were some challenges with the cytoplasmic inclusions in the modules. So what are cytoplasmic inclusions? When the cell creates products, say it is a melanocyte, which is in the skin, it produces melanin. Melanin is a protein, and then that melanin is going to be enclosed in the, a vesicle. And that vesicle is called a cytoplasmic inclusion, all right? Or it could be in the liver cell that will convert glucose to glycogen and then store it in a vesicle, and then you have the cytoplasmic inclusion. The difference between cytoplasmic inclusions and organelles, which are also membrane bound, is that cytoplasmic inclusions are temporary, right? You can use up the glucose or you can use up the melanin, but it's still a membrane bound organelle, but it's temporary. So those are the cytoplasmic inclusions, right? They are temporary, even though they're still membrane bound. The mitochondria is always going to be there. It's membrane bound, is always going to be there. The endoplasmic reticulum is always going to be there, right? It doesn't vanish at certain times. But cytoplasmic inclusion is kind of like reserved for those organelles that, get used up, right? Because of what's in them, right? So cytosol, fluid, part over there, and then sort of organelles suspended in there by the cytoskeleton, which is those microtubulins and actin filaments and so on. All right. So we'll start with the nucleus and then move on to the next. So there's two kinds of these organelles. Some of them are membrane bound, most of them are membrane bound, and a few are not. Like the centrioles are not membrane bound, and the ribosomes are not membrane bound. All right. So we all know about all these Golgi bodies, peroxisomes, lysosomes, and the smooth endoplasmic reticulum. Centrioles and ribosome are not. In fact, ribosomes are kind of sort of like a subunit like this, two subunits like that, and then over here will be the messenger RNA. All right, it's kind of attached to one of the subunits, and then another subunit is where you enter the RNA with the 3 codon bases like that. So this will be the RNA, transfer RNA, right? And so ribosomes is where produces this. Okay, so we'll talk about them in a minute. Because some of them are free ribosomes, some of them are attached to which organelle? Endoplasmic reticulum, in which case we call it rough endoplasmic reticulum. It's studied them as well. And then we'll talk about the function of that too. So the major organelle, of course, is the nucleus. And the nucleus is it's like the mitochondrion in that it is a double envelope as well. Remember? And then it's got the nuclear pores to let out the messenger RNA during protein synthesis, right? Okay, and then of course the DNA inside of the nucleus is going to be double-stranded, number one. It's going to be coiled, then it's going to be attached to proteins called histones, and those proteins plus the DNA together is chromatin. Remember when I said last time the DNA doesn't appear by itself? Why? Because you want to protect it. It's almost like clothing yourself. Like when you come out, you don't just come out naked. You get all the sun on you, for one, but you also get embarrassed because it's not cool. But same thing with the DNA, it's going to be dressed in all these proteins to protect it, so that we can protect it against mutations. And then of course the double envelope too is going to protect it even more. So the only time it unfolds and it forms chromosomes is when we're doing what? Cell division, right? When we're dividing the cells so that we have the equal genetic material on both sides of the poles during the division. So it becomes chromosomes, and the chromosomes will have two sort of chains on it called chromatids, all right? And the chromatids are attached by a centromere. And the centromere is never central. It's always to one side. That's how it is. You never see two chromosomes, two chromatids attached at the center, like a bow tie. No, never. In fact, if it's like that, sometimes those becomes non-functional, and it causes problems with creating the correct proteins. That the body prefers it like that. So I guess it's the way that the spindles, which we'll talk about in the end, move the DNA. Remember when the chromosomes are aligned at the equator? Those microtubulins I was talking about from the cytoskeleton and the centrioles are moving them around. So I guess it's optimal for them when the centromere is to the center, because the spindles attach to the centromere when they are moving the chromosomes during cell division. Okay, so the chromosomes, you know that, and then the centromere, of course, is this part that attaches the two sister chromatids. All right, that's the DNA in the nucleus. In the nucleus, we also have a dark staining part called the nucleolus, for singular, nucleoli, plural. That's where you form ribosomes. All these, both the subunits for ribosomes are formed there, and then you form also ribosomal RNA. Remember the RNA that attaches to the ribosomes in the cytosol, the free ribosomes, the ones that are not attached to the endoplasmic reticulum. And those free ribosomes make proteins that are used by the cell, because the proteins will not be contained in a vesicle, they'll just be produced and they go into the solution right away into the cytosol. All right? So that's what the nucleolus does. It produces the ribosomes and it produces the ribonucleic acid that is attached to ribosomes in the cytoplasm, right? Called ribosomal RNA, sometimes called RR, not sometimes, all the time called rRNA, and then tRNA is transfer RNA, mRNA, messenger RNA, the one that comes out of the nucleus, and then of course the ribosomes. That's where protein synthesis occurs. Even on the rough endoplasmic reticulum, protein synthesis is occurring on the ribosome, because the ribosome is one that attaches to the messenger RNA, right? Okay, so the rough endoplasmic reticulum makes proteins that are immediately wrapped in a vesicle and then transported out of the cell. Before that, they have to go to the Golgi apparatus so that they are put into the final folding structure, into the tertiary structure. Or sometimes the protein you add carbohydrates to make a glycoprotein. When you make it, you add a lipid, and that happens in the Golgi body. We'll talk about that in a little bit to form a glycolipid before it is shipped out. But free ribosomes synthesize proteins that the cell uses, because those proteins are already going to be into the solution, into the cytosol, and then they are used up by the cell. Rough endoplasmic reticulum makes proteins that are used by other cells that will be transported out. All right, so rough ER, rough endoplasmic reticulum, what's the major function of it? What's the major function? I've just been talking about it many times. What's the major function of the rough endoplasmic reticulum? Protein synthesis, because it's attached to the ribosomes. Protein synthesis. Okay. There's two types, right, of the endoplasmic reticulum. The one that's rough, which is said is studied with ribosomes, and is for protein synthesis, and then the one that's smooth. The one that's smooth is for lipid synthesis and carbohydrate synthesis. So usually you associate smooth with something that's sleek, like oil is smooth. So that's lipid synthesis and carbohydrate synthesis. And the one that's rough, well, protein synthesis. All right. So that's how you tell the two apart. All right. So rough endoplasmic reticulum, protein synthesis. Smooth endoplasmic reticulum, though, differs in specific function based on the organ. Like for instance, in the liver, it is involved in making lipids and making glycogen, carbohydrates. Okay, and then but in the muscle and in cardiac muscle and skeletal muscle, the smooth endoplasmic reticulum is used to store calcium. Okay, that's the only situation where the smooth endoplasmic reticulum is not totally faithful to its actual function, which is lipid and carbohydrate synthesis. Right? And if you look at the testes, what happens in the testes? The smooth endoplasmic reticulum creates steroids. Like testosterone is a steroid. And we said the steroid is what kind of compound? Among the four? Yeah, lipid. So that's lipid synthesis. So in the testes, the smooth endoplasmic reticulum forms steroids. All right? But in the small intestine, what happens is that when you digest the fats and you get all the fatty acids, the smooth endoplasmic reticulum in the intestinal cells will reassemble it first, will reassemble all those fats into all those fatty acids into fats, and then attach them to proteins, huge proteins called the chylomicrons. The product is called a chylomicron, where you have a bunch of fat and protein on it, just to make it soluble so that it can move through blood. All right. So that's what happens in the small intestine with the smooth endoplasmic reticulum. Okay, in the exam, usually I'll ask you, what is the function of the smooth ER in the testes? What is the function of smooth ER in the liver? What is the function of smooth ER in the intestines or the testes or skeletal muscle? Okay. All these functions include some sort of carbohydrate, lipid, synthesis, except for the skeletal muscle where it stores calcium. Calcium is what attaches to the proteins that are involved in contraction, muscle contraction. All right. So I don't know these functions of that. And then Golgi apparatus, we said in the cell you will find the Golgi apparatus in close proximity to what? Organelle? To the rough ER, right? Remember the rough ER makes those proteins and so forth. And then when it makes those proteins sometimes you have to fold them up, or you have to add a glycogen molecule on there to form a glycolipid, or a carbohydrate chain, or whatever it is, or a lipid chain to form a glycoprotein, or a lipoprotein, and so forth. So all that happens in the Golgi body or Golgi apparatus before it is packaged in a vesicle again and transported out. Okay, so that's the function of this. So that's why it's always in close proximity to that, because it processes the proteins into the tertiary structure, okay, or the quaternary structure when we have multiple folded proteins working together. All right. So that's the goal. All right. Lysosomes is a membrane-bound organelle that contains enzymes. Most of the time, the enzymes in the lysosomes are involved in breaking away products, cellular debris, or worn out red blood cells, things like that. Also, detoxifying substances. So digest bacteria as well, and viruses and toxins. Okay, degrade non-functional organelles in cellular debris, break down glycogen, and so forth, release thyroid hormone. Okay, non-useful tissue, and that's been recycled and so forth. Red blood cells are broken down by those lysosomes as well, inside of those macrophages. The bone is broken down by lysosomes as well. in osteoclasts, and they are stimulated by PTH, parathyroid hormone, and then to finish calcium. So they say you need calcium, and you're not taking enough calcium outside. And so lysosomes, of course, are going to be found in white blood cells and all those macrophages, and immune cells, and melanocytes too, to break down all these foreign microorganisms. Right? The specific function of these membrane-bound organelles that are called peroxisomes, they still have enzymes in them too, but they have oxidases that will get rid of free radicals. Free radicals are formed, they are highly, highly reactive particles that have an unpaired electron. Electrons always occur in pairs. If we have an element that has one unpaired electron, it becomes very, very reactive, and it can damage tissue, cause mutation, and things like that. So peroxisomes are especially, made for that. So while they also break down fatty acids, amino acids, and hydrogen peroxide. Hydrogen peroxide is the byproduct of fatty acid, amino acid metabolites. When you break them down, you get hydrogen peroxide. And hydrogen peroxide forms other free radicals, such as the superoxide. Like this is the superoxide ion. Okay, this one here is a hydroxyl ion. Okay, I mean a hydroxyl radical. A hydroxyl ion will have a charge on it, and it will have that one extra electron giving it a negative charge. Right. So there are many of these highly reactive oxygen molecules that are taken care of by the peroxisomes. So you see the slight difference between lysosomes and peroxisomes, right? They're both membrane-bound organelles with enzymes in them, but peroxisomes specialize in getting rid of free radicals. All right? And then the mitochondria, of course, is the powerhouse. And the mitochondria has two membranes, just like the nucleus. But the other membrane inside does what? It forms the cristae. Okay? Which does what? What does the cristae, what does the folding in of the membrane inside do in the mitochondria? What's the reason? Why is it? Yeah, it increases surface area for oxidative phosphorylation. And one of the things that was in your LensMat modules, what do you call the space between the cristae here? Starts with an M. The matrix. Okay, it was in your module too. And you kind of got it wrong a few times. So that's the matrix inside there. Then it creates the area, right? So, and it's the only one with its own DNA. Only organelle that has its own DNA. It doesn't require any instructions from the nucleus to make any proteins. It makes all the proteins it needs by itself. Why? It's very important, right? Because the cell produces this, not the cell. The organelle produces ATP, the only kind of energy that the body needs, right? So it's important that it can create its own protein without having to go to do translation and all those processes in the nucleus. So it has its own DNA. It's the only organelle that has its own DNA. Alright? And then the last bit is the centrioles. The centrioles are, again, microtubules. They are rod-shaped proteins, alright? Except they occur in triplets. It's like 9 triplets surrounding, making a rod made up of these triplets. Okay? And those are strategically placed very close to the nucleus in an area called the centrosome. Okay, I think there were also challenges with this in the modules. So the centrosome is right next to the nucleus, and that's where you have these two centrioles normally oriented at right angles to each other. So you have a centriole like that and another centriole like that, and then they're located in the area called the centrosome, right by the nucleus. Why do you find these tubulins and these proteins, these centrioles, right by the nucleus? What happens? What do they do? What's the purpose of those rod-shaped proteins? The centrioles. They move the chromosomes at the cell division, right? those are the spindle fibers. They make up the spindle fibers that will, at the centromere, hoist all those chromosomes in line. So that's why they occur right close to the nucleus, right? And that area is called the centrosome. That carries those two centrioles right angles to each other. And each one will have a triplet of those tubulins. Right? And then so you get macrotubules that form the spindle fibers, hence the location by the nucleus, because they will line the chromosomes at the equator during cell division. Right? So very important. And also these ones form the basis of flagella in the cell, the cilia that we saw in that cell. Alright? For movement of cells or movement of substances on top of cells. Alright? And then quickly, microvilli, I think even in this class there was a problem between what's the difference between, in terms of function, between cilia and microvilli? We talked about it real quick earlier on. Cilia will do what? On top of the cell membrane. And then the microvilli will increase the surface area, so that's the difference, all right, between the two. And then the flagella is a tail-like projection that will move like a cell, like a sperm cell, for instance, through the uterine tube or the oviduct. Again, a summary of all the things we just talked about, all the organelles and their functions, right? So if you want to see them all in one. Thank you, guys. We'll see you in a little bit. We just went a little bit over by 5 minutes, but we got plenty of time between now and that. We'll start. Bye. Thank you, guys.